Refrigerant enters a pipe steadily at 200 kilopascal and 20 degrees Celsius with a velocity of 5 meters per second. The refrigerant gains heat as it flows and leaves the pipe at 180 kilopascal and 40 degrees Celsius. Determine the volumetric flow rate of the refrigerant at the inlet and mass flow rate of the refrigerant and the velocity and volumetric flow rate at the exit. Okay, so we are dealing with a pipe, a system. We know that it's a steady flow device and our system is a refrigerant. So we need to use refrigerant tables to solve this problem. Let's start with sketching the situation. So it's a pipe. Okay. And the pipe has 28 centimeter diameter. There's a typo here. So they are giving us the diameter. And at the entrance, it is 200 kilopascal, 20 degrees Celsius, 5 meters per second. It is always good to sketch this process, and because this way we can easily see what is going on. For example, here it also says there is heat interaction, that it gains heat. Okay, we should sketch that energy interaction too. So looking at our system, we have different energy interactions. For example, mass getting in, heat is getting in, and mass is getting out. Now let's take a look at what are they asking for. They ask for the volumetric flow rate at the inlet. So we can say at the inlet. Inlet subscript is 1 when we are solving this problem. You can also use subscript I. It is up to you. And they also ask the mass flow rate of the refrigerant. And velocity and volumetric flow rate at the exit. Okay, velocity at the exit and volumetric flow rate at the exit. So now let's take a look at how we can solve this problem. When they're asking for volumetric flow rate, to find it, there is one formula. Actually, several formulas. One of them uses area and velocity. If you can remember that. One way to actually find it is through this formula. Let me write it first. Another way to find it is using area and velocity. And in this case, initially we don't know the mass flow rate. We can probably find those specific volume and mass flow rate later on, because specific volume is the property of your system. At the inlet, you can look at the tables and find it. But they're already giving us the area and they're already giving us the diameter. So I know then I can find the area and I know the velocity. I can easily use this formula I have to calculate the volumetric flow rate at the inlet. So let's take a look at how we can do it. area from the diameter. Diameter over 2 is the radius squared. Pi times pi is the area. So I'm gonna write it. Instead of area, we write pi d squared over 4 and velocity. And now we formulated what they're asking for. We're gonna plug in the numbers we have. Times the velocity. So all units are in meters. Now, volumetric flow rate from inlet to exit can change. Density from inlet to exit can change. But what is not going to change for a steady flow is the mass flow rate. Okay. Inlet mass flow rate equal to exit mass flow rate equal to the mass flow rate. So there is one single mass flow rate throughout the pipe in a steady flow device with one inlet and one exit, in other words, a single stream. And to find mass flow rate, we have an equation that is 1 over specific volume times velocity times the area. Okay, so here we can find specific volume at the inlet because we have given the properties of the refrigerant, and we have already calculated this part, right? Velocity times area, because that was volumetric flow rate at the inlet. Now, in order to calculate the mass flow rate, you can either use second state, in other words, exit properties, or first state or inlet properties. In this case, we are just given inlet velocity, so I'm using inlet properties to calculate the mass flow rate. And if we plug in the numbers now, of course, to do that, first we need to look at the tables, right, to find specific volume. And let's do that in a new page. Oh, just a second. We add a new page like this. Good. Okay, so at the inlet, okay, the pressure is 200 kilopascal and the temperature is 20. So those conditions, at that pressure and at that temperature, your refrigerant is a superheated vapor. Now, if you're not very good at looking at the right tables, please listen to my recordings for chapter 3 and chapter 4, that where I in detail explain how to read the right tables. But in this case, I will just directly give you the answers from the right tables. But at this temperature, at this pressure, you have a superheated vapor. So you need to look at superheated refrigerant tables to read other set of properties. Of course, one of which is specific volume for the refrigerant. And for the exit, we are given the pressure is 180 kilopascal and the temperature is 40. And at these conditions, you should again have a superheated, and from the superheated tables, you should read the specific volume at the exit 2. With those readings from the tables, it will help us now to solve this problem very easily. If we remember what we were doing, we were trying to calculate the mass flow rate using specific volumes. Now I'm gonna do that. For specific volume at the inlet, I'm gonna write this volume. And we did already calculate what is area times velocity, and it was this volume right there. So I'm just gonna directly plug that in. All right, and then we find mass flow rate with the units of kilogram per second. Okay, so one of the parts of the question was to asking for finding the mass flow rate, and we did that too. Now they're also asking for volumetric flow rate at the exit and a velocity at the exit. Those are again easy to find. If you remember how you can actually calculate volumetric flow rate. Okay, remember always there is one formula, and then to calculate volumetric flow rate that uses mass flow rate, and that is volumetric flow rate is equal to mass flow rate times specific volume. We also had another formula, and we can write it here for your reference. If they are giving you area and velocity at the exit, you can also use those to calculate the volumetric flow rate. But since already we are given, we already found the mass flow rate and the specific volume at the exit, we can use that equation because we actually don't know what is the velocity at the exit. That's what we are trying to find out. So let's use mass flow rate. And specific volume that we read from the tables. And this should give us the volumetric flow rate at the exit. And then now we can find velocity again through the same equation here we have written, which is gonna be basically volumetric flow rate over the area. And to area is has the same diameter because pipe area throughout its length is not changing. So here we can just, I guess, just write pi. And this should give us 6.02 meter per second. Okay, I think we did something wrong here with the units. That's why the units looked funny for a second. Now I realized. Okay, so this is volumetric flow rate, right? Meter cube per second. Now it makes sense. The final unit is meter per second. So we also found the volumetric flow rate at the exit, and then we found the velocity at the exit. Very good. Refrigerant at 700 kilopascal and 120 degrees Celsius enters an adiabatic nozzle steadily with a velocity of 20 meters per second and leaves at 400 kilopascal and 30 degrees Celsius. Determine the exit velocity and the ratio of the inlet to exit area. Let's start with our sketch of a nozzle. Remember, the purpose of the nozzle is to increase the velocity at the exit by reducing the cross-sectional area. Now we are talking about a refrigerant. And initial conditions at the inlet is 700 kilopascal. Okay. And we also 120 degrees Celsius. And this is an adiabatic nozzle. That means there are no heat interactions here. And actually we also are given the velocity at the inlet. Let's read it carefully. Okay. Exit pressure dropped and 30 degrees Celsius. Okay, so they're asking for the exit velocity, ratio of the areas. Now, how we can find those? First of all, our system is a steady flow device, which is a nozzle, and here the kinetic energy is important because that's the whole purpose, is to change the kinetic energy. So if we want to make an assumptions, we can assume potential energy changes are negligible, but kinetic energy changes are important. No heat interaction, no work interaction. So only energy interactions are mass getting in and out, and it's carrying energy with it, and energy it carries with it related to its enthalpy and kinetic energy. Now, but let's talk about how we can find the velocity at the exit. So there are ways. For example, if you know the mass flow rate equation or volumetric flow rate equation, for example, remember this is, let's say, at the exit. Now, if we want to find the velocity, we need information about the area and then the volumetric flow rate if we are going to use this equation. Therefore, this equation will not work. Another way to find the velocity is the energy balance equation, because in the energy balance equation, we have also the kinetic energy term. So what we are going to do is, first of all, let's write mass balance, inlet mass flow rate equal to exit. There is a single mass flow rate because it's a single stream, one inlet, one exit. Energy balance is for a steady flow device, since the energy of your system, which is a nozzle, right, and a control volume, and it doesn't change with respect to time. That means energy that gets in has to be equal to what energy getting out, keeping the energy of your system the same with respect to time for a steady flow. So with that being said, let's write down the energy balance formula and see how we can figure out the velocity at the exit from there. So as we talked about, energy is getting only with the mass, and energy of the mass is related to its enthalpy and kinetic energy. One important observation here is that Since it's a single stream in this energy balance, mass flow rate cancels out. So now we only have to deal with enthalpies and kinetic energies. And let's write it down. You can directly solve this equation for V2 and do a calculation, or other type of arrangements to this equation is also fine as long as you know what you're looking for. So I'm gonna arrange it in this manner and I'm gonna solve it for V2. All right, actually let's solve it for V2 and see how it's gonna look like. And then we also have to remember something very important, that the unity conversion ratio that we need to use here, because kinetic energy unit is meters squared per second squared, but we need to convert that to kilojoule per kilogram. Let's not forget that. For that, we need to multiply the kinetic energy with a unity conversion ratio of 1 kilojoule per kilogram is equal to 1000 meters squared per second squared. And we have to do it for both kinetic energies. Simply, you can write the denominator is 2000. Because it is 2 times 1000 denominator is. So let's do that. Let's solve it for V2. How can we do it? Let's think about it. I think that is the right way. So this gives us now, of course, to solve this, we need to know what H1 and H2 is, and we need to look at refrigerant tables. So therefore, let's do that in the next page. When we plug in, when we look at the tables, initially it was 700 kilopascal, and then the temperature was 120. You look at superheated tables to read what is specific volume. You need to also read enthalpy to use it in the energy balance. For the exit, we are given the pressure 400 and the temperature to be 30. Looking at superheated tables, specific volume at the exit is this. And enthalpy is this. All right, now we know that our properties of the system at the inlet and the exit. This is gonna help us to solve what they're asking for. We have already formulated how to solve for the velocity. So let's go back to that. Let's copy this and solve it in the next page. So now let's plug in the information together. 358.92. So velocity was 20. H2 was 275.09. Okay. Okay, and if you solve for the velocity, it is going to give you 409.9. Very good. So the next thing is we found the velocity at the exit. Next thing, they're asking for the ratios of the area. Well, you need to think about here, how can you find that? Ratios of area. If you remember, the mass balance here is this, right? That means that inlet mass flow rate is equal to exit mass flow rate. And we can have a way to write the mass flow rate that includes the area. For inlet mass flow rate, we can write this. And for exit mass flow rate, we can write this. And if we actually rearrange this to solve for the ratio, we can find the value of the ratio of the areas, right? Let's solve this for A1 over A2 as the question asks for. It's gonna be V1 over V2, V2 over V1. All we have to do is now simply plug in specific volumes correctly. And then velocity, correct, right? This way you can solve the ratio. $15.65. An adiabatic compressor compresses 10 liters per second of air at 120 kilopascal and 20 degrees Celsius to 1000 kilopascal and 300 degrees Celsius. Okay, let's start with sketching our compressor. Compressor always requires a power input. And to increase the pressure of a flowing fluid. Okay, so initially they give us volumetric flow rate. And they give us 120 kilopascal. Temperature 20. And they give us at the exit, it is, again, you can use a subscript of E for exit or 2 for the exit. Both are fine as long as you know what you're defining. So see a compressor with the power input. It is increasing the pressure and it is increasing the temperature of air in this case. They are asking for, in order to achieve that property change in the air, what should be the power input? And they are also asking for, so the first thing they're asking for is actually work required by the compressor in kilojoule per kilogram, which is this, and also the power, and which is this. Okay. All right, so let's start with energy balance, and remembering this is a steady flow device, and we also know that it's adiabatic. There is no heat interaction here. Only energy interactions I can identify here from what is given. Mass is getting in and out. Also, we have a power or work getting in. And therefore, we can start with writing the mass balance and then energy balance and see where it's going to take us. So mass getting in is equal to mass getting out, single stream, one mass flow rate. Let's write down our energy balance for a steady flow device. Energy is getting in with mass. Here, of course, we are not given any velocity or elevation. We can assume those changes in kinetic and potential energies to be zero. Therefore, do not include those in our energy balance. And we have energy getting in with work. In other words, in this form of energy balance, we use power. And it is also getting in with mass. And its energy is related with its enthalpy, getting out with mass. So in order for us to find the power, all we have to do is actually solve this equation. Looking at what we know here, we don't know the mass flow rate. They are instead giving us volumetric flow rate. So there is a hint there that we have to use the volumetric flow rate to calculate the mass flow rate. And remembering this is air, ideal gas, so we can use Cp, Cv, specific heat, and ideal gas equations. Or we can also look at table A17 if we know the temperatures. So all those options are available. You can either look at table A17 because it is air to read enthalpy H1 and H2. And you can also replace delta H since this is gonna be. And remember not to do that for refrigerant or for water because this is for an ideal gas only. So instead of delta H, which is the specific enthalpy change of the air, I can write this. Okay, so specific heat, and then now we can use that equation to solve it, but we need to do some simplifications here because we don't know the mass flow rate. So what we can do is divide both sides of the equation to mass flow rate, and therefore this is directly gonna give us the work in per unit mass is equal to Cp delta T. Right. So in this case, a question that can come to mind is which volume we are going to use for the specific heat at constant pressure. And if we know the temperatures in both inlet and exit, if that is given to us, the best way is to average those temperatures and then read the corresponding specific heat from the tables. So looking at the temperatures, 300 degrees Celsius is 573 Kelvin, and 20 degrees Celsius 293 Kelvin. If you average the temperatures, and find an average temperature, which is going to be in this case 433 Kelvin. Now the next thing is you need to go to table A to B to read the corresponding specific heat at that temperature. So we go to the table for different gases, air, carbon dioxide, carbon monoxide, hydrogen, nitrogen. We use this table, right? So in that case, we are looking for the specific heat at 433 Kelvin. So somewhere in between these values, if you do interpolation, you're going to find specific heat to be 1.018 kilojoule per kilogram Kelvin. Okay. So therefore, let's solve it. We were trying to solve it for the work per unit mass using specific heat. And temperature change. The unit doesn't matter in temperature change, remember. And therefore we calculate this to be 285 kilojoule per kilogram. So this was the first part. Now they are also asking for the power. And to be able to calculate the power, we need the mass flow rate, because the power is equal to mass flow rate times work per unit mass. So if I can find the mass flow rate, I can find the power. To be able to find the mass flow rate, since they give us volumetric flow rate, it's a hint in the question. We can use volumetric flow rate and divide it to specific volume to find the mass flow rate. Since inlet conditions are given, we can use the inlet conditions to find this. But yes, we know this volumetric flow rate, but we don't know the specific volume. But for an ideal gas like air, it is very easy for us to find specific volume, because we can use ideal gas relation for the first state, in other words, inlet state. This is the ideal gas constant for air, which you can find from table A1. First state temperature. What's going on? Okay. And then pressure has to be in kilopascal. If you solve it, you're going to find this. Now we can use that to calculate the mass flow rate. This is given to us. This is what we calculated. And 0.01427. Now mass flow rate is known. We can simply calculate the power. Mass flow rate times specific heat times delta T, which is already calculated to be 285 kilojoule per kilogram. And of course, we find it in terms of kilowatts. And this concludes our solution. Carbon dioxide enters an adiabatic compressor at 100 kilopascal and 300 Kelvin at a rate of 0.5 kilogram per second and leaves at 600 kilopascal and 450 Kelvin. As we always do, we sketch and write down what is given and making sure we know what system it is, how it works, right? Compressor always works with a power input. Okay. And then what is given is a CO2 gas, an ideal gas. Adiabatic means there's no heat interactions here. Enters with 100 kilopascal and 300 Kelvin at a rate of 0.5 kilogram per second. So what they are giving us is mass flow rate. We understand from the unit, right? Mass per time. So that's a mass flow rate, 0.5 kilogram per second. And since this is a steady flow device with one inlet, one exit, mass flow rate throughout the flow doesn't change. And from inlet to exit, it is the same. So the next thing is the exit properties, 600 kilopascal with 450 Kelvin. What are they asking for? It says, please neglect kinetic energy changes, okay? And we don't also see any potential energy change. Therefore, we can also neglect that one too. And then determine the volumetric flow rate of carbon dioxide at the inlet. So, volumetric flow rate. So, let's see. And the power input. So power, if they're asking for a power, one way that comes to my mind is to write the energy balance. If they're asking for the volumetric flow rate, we might be able to find it from specific volume and mass flow rate. Since they didn't give us any area and velocity, we cannot use those equations here. So if we look at it, how we can find the volumetric flow rate at the inlet, we can utilize this formula. As we always do, we check it and we know mass flow rate is given. For specific volume, for ideal gas, we can use the ideal gas formula. For R, we need to look at table A1 for the carbon dioxide, we need to find R. Temperature is 300 and the pressure was given to us as 100 kilopascal. And with that we calculate this volume to be like that. Okay, and now let's multiply this with mass flow rate. Therefore, calculating the volumetric flow rate. So the next part, they were asking for the power, and if they're asking for the power, we need to write the energy balance. Since this is a steady flow device, energy balance is the rate of energy getting in has to be equal to the rate of energy getting out. So just like that. And therefore, when we look at our sketch, we can see the energy interactions here. Mass is getting in, power is getting in, and mass is getting out. Since there are no heat interactions, and there's the only work interaction is the work getting in, we can simply write our energy balance. All we have to do is now to solve this. Let's first rearrange this equation. So instead of enthalpy change, we can write Cp delta T. Now looking at the temperatures they give us, 300 and 450. We can average those temperatures and find an average temperature. That is equal to 375 Kelvin. Now for the average temperature, we're gonna look at our table and read the corresponding specific heat. We need to find the right column, right? Where is it? Carbon dioxide. So here. Now we are looking for specific heat and our temperature was 375. So somewhere in between this volume and this volume, if we do interpolation. And if you do the interpolation for for this temperature, Cp for carbon dioxide is 0.851. Now let's plug that in and calculate it together. So the mass flow rate is 0.5 kilogram per second. And specific heat is this. And we also have the temperature change, right? This should give you approximately 64 kilowatts. Steam flows steadily in a turbine with a mass flow rate of 26 kilogram per second with negligible velocity at 6 megapascal and 600 degrees Celsius. As we always do, we sketch a turbine and we remember that turbine generates a power output using the energy of steam. Okay, let's delete that. And they are giving us 6 megapascal for pressure and 600 degrees Celsius for the temperature in the steady flow device, that is turbine. And then there is one single mass flow rate, since one single stream, one inlet, one exit, and they are giving it to us. Steam leaves the turbine at 0.5 and 200 degrees Celsius with a velocity of 180. So at the inlet it's negligible, but at the exit it is 180. The rate of work done by the steam measured to be 20,350 kilowatts. Good. The turbine is also losing heat during this process. It's not an insulated turbine, so there is also a heat interaction. And if the elevation change is negligible, that means set potential energy change to 0. Determine the rate of heat transfer associated with this process. So we can also say this one too, because it says initially a negligible velocity. Okay, so with our assumptions and realizations, now our problem is very clear. Let's take a look at what they're asking for. They're asking for the heat interaction. So only way to find it is simply write the energy balance. That's not very difficult. So since this is a steady state device, energy balance is the rate of energy getting in equal to getting out. Here we need to be, when we are writing the formula explicitly, we just have to be very careful with the energy interactions. The energy that is getting in is the mass, energy with the mass. But others are getting out, like the power and the heat interaction. Let's put the rate of heat transfer rate. And then power, heat transfer rate, and then the mass getting out. So only energy that is getting in, energy that is getting in with the mass, which is mass flow rate times enthalpy times velocity 1 squared over 2, which is getting out is heat, power, and energy with mass. One thing to remember here, we made an assumption to this to be 0. So don't forget that. So therefore, if we look at it now, how we can solve it for the Q, we need to find, because mass flow rate is already given, we need to find enthalpies, and I think other terms are already given to us, so we just have to plug in everything we know, being very careful with which we need a unity conversion ratio here. We just need to be very careful with that, but other than that, it just requires us to plug in the numbers. Now, after we formulate our energy balance, to be able to solve it for the heat, we need to plug in the numbers. And for H1 and H2, we need to look at them from the tables. So for pressure 6 megapascal and temperature at the inlet to be 600 degrees Celsius. From steam tables, we read enthalpy at the inlet to be this volume. So from the same tables, we look at for the pressure 0.5, I mean water tables. We look at temperature to be 200 and our enthalpy is this. So since now we know the enthalpies, let's plug in the numbers and then solve it. Okay, first one, mass flow rate times. So I'm not gonna use the units because it's gonna make the equation very crowded, but you just need to be very careful in the sense that we need to multiply this kinetic energy term, as we discussed before, with the unity conversion ratio of 1 kilojoule per kilogram is 1000 meters squared per second squared. So for that reason, the denominator becomes 2000. So you just need to remember that when you are writing the equation. Okay. So let's do that. All right. So mass flow rate is 26. And then H1 is right, and then this is equal to Q out. Power is already given to us. And this equation continues. Mass flow rate is 26. And H2 is this. We need to add the kinetic energy to this. Don't forget that. And if we do the equation and solve it correctly, the heat should be around 105 kilowatts. 105 kilowatts. Okay. Refrigerant at 800 kilopascal and 25 degrees Celsius is throttled to a temperature of -20. So we are dealing with a throttling valve, and then we know what it does. It restricts the flow, drops the pressure, drops the temperature. Determine the pressure and internal energy of refrigerant at the final state. Okay, so first of all, let's sketch it. And let's take a look at what they are giving. Maybe it's a valve. Oh, like this. So we are talking about a refrigerant. Its pressure is known, its temperature is known, and at the exit its temperature is known. Determine the pressure at the exit. Final state means it exit, and then the internal energy. I believe they meant specific internal energy, which is something we can find from the property tables. Now, with that being said, since they're asking for pressure and internal energy, these are systems properties, and we should be able to look at the tables to read those. Before that, let's make our assumptions. In a throttling valve, we know that there is no work interaction and no heat interactions unless those are stated by the problem. It is safe to assume no work interaction, no heat interaction, only mass is getting in and out in one single stream. So one single mass flow rate throughout, and we also know the enthalpy at the inlet is equal to the enthalpy at the exit, which comes from the energy balance we learned in our lectures. So whenever or as soon as we solve a throttling valve, we have to remember this condition that came from the energy balance. So therefore, if I know at the first state what is the enthalpy, and then we can able to figure out what is the enthalpy X at the exit. So at 800 kilopascal and 25 degrees Celsius, we have a compressed liquid. So H1 is approximately HF at, it's really bad writing. Okay, it's 25. We look at the temperature tables to read saturated liquid enthalpy. Now for this, this has to be equal to the exit enthalpy. Now let's take a look at the exit. If at the exit we have minus 20 degrees Celsius with specific enthalpy of 86.41, now we can look at the tables because we have given two properties, and apparently it is actually a mixture because the enthalpy value you have at minus 20 degrees Celsius is in between HF and HG, which makes sense. Then we have a mixture. Let's write it down like this. That's why it's a mixture. When it is a mixture, the pressure has to be the saturation pressure because that's the only way you can have a mixture at those conditions. It is something you read from the same table. So this way we were able to find the pressure directly because it's a mixture. But when it comes to other properties like specific internal energy they're asking for, you just need to calculate the quality first, because once we calculate the quality, we can only then calculate internal energy through this equation at minus 20 degrees Celsius. So only way to calculate quality first is through a known property, specific property, and the only known property in the second state or the exit state is the enthalpy. So I'm gonna use enthalpy to calculate quality through this equation. Now we know that, let's calculate the internal energy. Why this never works with me? Okay. So you should find 80.7 kilojoule per kilogram. All right, that's it. An adiabatic capillary tube is used in some refrigeration systems to drop the pressure of the refrigerant from the condenser level to the evaporator level. The refrigerant enters capillary tube as saturated liquid at 50 degrees Celsius and leaves at minus 20 degrees Celsius. Determine the quality of the refrigerant at the inlet of the evaporator. So inlet of the evaporator should be the exit of this capillary tube. Okay. If you want to remind yourself how capillary tube is used in refrigerators, I'm sorry, you might want to watch the video we have watched from the YouTube in the lecture. Please check your canvas. Now, let's take a look at what we are dealing with. What is our system, and sketch it. Now we have a capillary tube, which is a throttling valve, and in this case we have one inlet, one exit in this steady flow device. Now we are dealing with a refrigerant. In this case our system is a refrigerant, and it enters as a saturated liquid at 50 degrees Celsius and exits as minus 20. So again, we remember, what does a capillary tube do? It restricts the flow and drops pressure, drops temperature. Now determine the quality at the inlet of the evaporator. Again, meant that exit of the capillary tube. So again, as soon as you see a throttling valve, we remember the condition that this is true for a capillary tube with the assumption no heat, no work interaction, one single stream, only mass interactions, mass getting in and out. That makes the enthalpies of the inlet and exit equal to each other. So it is very easy now, because all we have to do is look at the refrigerant tables for the first state or the inlet state. We have a saturated liquid at 50 degrees Celsius. We can just look at refrigerant tables and read the enthalpy to be, not exactly equal to, actually. At that temperature, 123.52. Okay, and at the exit, this is the same enthalpy, So minus 20 is the temperature, and enthalpy is 123.52. Now this should give you it's a mixture, because it's a hint there's already a quality they're asking for, but the properties can also lead you, like it is being minus 20 and the enthalpy 123.52. This should also tell you you have a mixture. So to calculate the quality, we need to use the only known property, which is enthalpy. And if we do that, looking at the tables at minus 20 degrees Celsius, reading what is HF, what is HFG. You should be able to calculate quality to be this. And it is unitless. Hot and cold streams of a fluid are mixed in a rigid mixing chamber. Okay, so this is a mixing chamber question. And let's start sketching it. Our mixing chamber. Oh. Okay. So mixing chamber has two inlets, one exit, and it's a steady flow device. And we need to identify clearly the flow. It's like the shower example, right? Shower is also a mixing chamber. So hot fluid getting into the chamber with 5 kilogram per second mass flow rate. Let's give some numbers to inlets and exit, not to make mistake in our calculations. And the energy in the amount of 150 kilojoule per kilogram. So they are telling us what is the energy of the fluid per unit mass, in otherwise theta. So the cold one, it flows with a mass flow rate of 15 and energy of 50. Okay. There is heat transfer to the surroundings from the mixing chamber. This is not a well insulated system. As I always tell you, if it's stated by the problem, then you cannot ignore the heat transfer. There is a heat transfer to the surroundings from the mixing chamber in the amount of 5.5 kilowatts. Determine the energy carried from the mixing chamber by the fluid mixture per unit mass of fluid. So they're asking for this one. So the only way to find energy carried with the fluid per unit mass is writing our energy balance, and it seems like they already give us a lot of information for that. Again, first of all, we understand steady flow device. We start writing with the mass balance. In this case, mass balance has to be sum up all the inlets, has to be equal to exit, because the water streams from 1 to 2 is connected. They are merging and making a one single exit. Therefore, we need to sum those up. And actually we can directly find, because this is 5 kilogram per second and this is 15, we can actually solve our mass balance just like that. and this will give us the exit mass flow rate. Now, with that being said, let's write down the energy balance, because we know in a steady flow device, energy getting in is equal to energy getting out. When we look at it, we see energy interactions such as energy getting in from number 1, energy getting in from number 2, energy is getting out by heat, and energy getting out from number 3 as mass. Therefore, an energy in inlet 1 and inlet 2 is different, because those are two different streams. Therefore, let's now formulate our energy balance. Energies are getting in from the first inlet and getting in from the second inlet and getting out as heat and getting out as the energy of the fluid. So they're asking for this term. What can we do? We can solve this energy balance, because they already give us everything here. Okay. I'm not gonna actually write the units, or maybe let's write it, because this is an interesting question where they give us the energy per unit mass. So do you can guys see how units actually cancel each other and give us what we are looking for? So the mass flow rate is 5 kilogram per second. Energy per unit mass 150 kilojoule per kilogram. See, when we multiply these units, it gives us kilojoule per second, which is energy flow rate. And mass flow rate at the inlet 2 and energy is 50. This is equal to heat. Heat is already given too, right? So we can check 5.5 kilowatts. Kilowatt is kilojoule per second. So the units match. We just have to write 5.5. And mass 3 is 20. All right. So if you solve this, and you should get 74.7 kilojoule per kilogram. But I want to remind some important information for students who might be listening and cannot understand what theta is. So theta is the energy of the flowing fluid per unit mass, and it is made up of the enthalpy of that fluid, and then kinetic, and then potential energy. And many times the kinetic and potential energy changes in energy balance is negligible, so usually the theta is represented with enthalpy. But we need to be careful. If there is velocity, elevation, those terms has to be included too. So just wanted to remind you, but theta represents the energy of a flowing fluid per unit mass. Air is to be heated by hot exhaust gases in a cross-flow heat exchanger before it enters the furnace. So now we are dealing with a heat exchanger problem. Heat exchanger is also a steady flow device where we have two fluids, but unlike the mixing chamber, here the streams are not mixing, okay? For each individual stream, there is one inlet, one exit. They are just exchanging heat without mixing. So in this case, we have two different systems, one of which is air. The other one is the exhaust gas. And we are given the specific heat values for those gases. And again, let's look at how air enters. Air enters at 95 kilopascal and 20 degrees Celsius as it's sketched at a rate of 0.6 meter cube per second. So they are giving us volumetric flow rate too. If you want, you can write it like this. Determine the rate of heat transfer to the air and its outlet temperature. So air is going to exit from this direction. They're asking for its temperature at the exit and then the rate of heat transfer to the air. So from the exhaust gases, there will be heat getting into the air. So now, as I always say, you need to beautifully sketch this problem and label all the inlets and exits with numbers so you know what subscripts will represent, such that this is going to be inlet 1, exit 2, and from the sketch behind this exhaust gas exit, which should be number 4, and there should be some here inlet number 3 behind. Okay, now with that, what can we do in this problem? They're asking for a heat interaction between the two streams, so we need to write energy balance either for the air or the exhaust gas and solve it. Now what we can do is let's write the energy balance on the exhaust gas. Okay, so what is going to happen? We just need to remember they actually give us some other things here that we didn't plug into the sketch because I thought they already sketched it there, but the combustion gases enters at 160 degrees Celsius at a rate of 0.95 kilogram per second. Here they give us the mass flow rate and then also the inlet temperature. What we can do is, before we actually go ahead and directly write the energy balance on the exhaust gas, you should take these steps. Initially, you should write the mass balance. So we have a single stream for each mass flow. So mass flow of air. And then we have exhaust gases, right? It has its own stream and it is like just like that. Let's write E. Okay. Now, when it comes to energy balance, we are not going to write the energy balance in the whole heat exchanger because they're asking for heat interaction between the systems, air and the exhaust gas. So I'm gonna try to write down the energy balance on the exhaust gas and see if I can calculate the heat that is getting out of it to the air. So for the exhaust gas, there is energy getting in from number 3. But let's start with, actually maybe some of you will get confused. So this is an energy balance, just reminding ourselves for the steady flow device, just like a heat exchanger, and energy getting in with the mass, and energy is getting out with heat and mass. So actually, if you zoom in and try to sketch the exhaust gas, if this is the stream of the exhaust gas, it is losing heat, right? And this is the system boundary, and exhaust gas mass flow rate coming in here with this volume, they give it to us, and then exiting with the same mass flow rate and losing heat, while air is flowing around it. Let's say air is green, right, around it, and it is absorbing that heat from the exhaust gas and heating up. So with that understanding, now the energy balance makes sense, because only mass is getting in from inlet 3, and from exit 4 it is exiting. Okay, so instead of M3 and M4 we can write ME. Since they're asking for Q out, I'm just gonna solve it for Q out. Heat flow rate in the parentheses. Okay. Now, since this is an ideal gas, what I can do is, instead of enthalpy change, I can write, and this is also a hint from the problem because they give us the specific heats, and this is gonna be just like that. Now, mass flow rate of the exhaust gas is given to us. In addition to that, they give us the specific heat too. If you look at it, 1.1. Again, the degree change, it can be degrees Celsius or Kelvin. It doesn't really matter because it's a temperature change. You can keep it degrees Celsius if it feels comfortable for you. And then, and the temperature at number 3 is 160. Let me move this a little bit, this direction. Okay, right, 160 minus the exit 95, right? So therefore here in this situation, as you might notice, labeling the inlets and exit with correct numbers are very important. So it prevents you from making any mistakes. So this is the heat interaction they're asking for, and we found it. The next thing we need to find is outlet temperature. Well, one way that comes to my mind is maybe this time, instead of writing energy balance on the exhaust gas, we can write the energy balance on air, because the heat that is getting out from the exhaust gas is actually what is getting in to our air. So therefore we can write this time, it's going to be the same heat interaction, because as I said, the heat getting out of the exhaust gas has to be equal to heat that is getting in to the air. And they are gonna be the same term in the energy balances. It is gonna be in energy getting in instead of getting out. Okay, so here if we write it, this time mass getting in H1, heat getting in and mass getting out. And if you take a look at it, it is gonna be H2 minus H1, which is going to be like okay. Delta H, instead of that we can write Cp T2 minus T1, and Cp specific heat, they already give it to us. Temperatures, they already give it to us, temperature 1. We're gonna figure out temperature 2 from here using the same heat. So all we have to do is plug in, but there is one thing here we need to remember. They didn't give us mass flow rate for the air. Instead, they actually gave you volumetric flow rate. I think there is one way to do this. Mass flow rate is equal to volumetric flow rate over specific volume, and specific volume can be found from the ideal gas relation, right? It is going to be RT1 over P1. So in other words, if you want to find the mass flow rate, it is P1 volumetric flow rate over RT1. Okay, so we just need to therefore plug in the values we have. 95 kilopascal is, if you look at it, given to us for the pressure. So that, and then volumetric flow rate is directly given to us. And R is for the air. And the temperature is given. With that, mass flow rate should be 0.6778 kilogram per second. Now we're ready to plug this in and then calculate from this equation. Let's copy, not this one. Let's copy this part like that. And go down and let's solve it. Q is 67.93 and the unit is kilowatts, so kilojoule per second. Mass flow rate is this, kilogram per second. Specific heat, they directly give it to us. Let's see. Yes. And then temperature is what we are trying to figure out, and at the inlet it was 20 degrees Celsius. Let's check it. Correct. Okay, so if you solve this for T2, it should be 120 degrees Celsius. It is good because air temperature is expected to increase due to the heat interactions with the exhaust gases. A 0.3 meter cube rigid tank is filled with saturated liquid water at 200 degrees Celsius. A valve at the bottom of the tank is opened and liquid is withdrawn from the tank. So looks like this is a rigid tank where we have this, where we are discharging a certain substance, and as a function of time, the mass of the water inside will decrease. So then we can call this an unsteady flow device. Heat is transferred to the water from the surroundings such that the temperature in the tank remains constant. Determine the amount of heat that must be transferred by the time 1/2 of the total mass has been withdrawn. So it decreased by 1/2 after we withdrawn the water. Alright, so first, as you notice, we identified this as unsteady flow device. Once we know this, we can start writing our mass balance, energy balance, and then move forward from there. But they're asking for heat interaction, so the only way to find it is from energy balance. Okay. So let's write the mass balance. In minus out, getting in mass minus getting out mass is equal to the change in the energy of the mass of our system. Again, this is called mass balance because on the left hand side we have mass interactions, right, getting out, that is causing a change in your system's mass. Let's say, okay, so I'm gonna explain this formula by giving numbers, okay? Initial mass was 10, 3 kilogram is withdrawn, final mass will be 7. So it is that simple, right? And there is no inlet mass here. So our formula is actually gonna simplify into, let me erase these. If we give up some numbers to understand this formula, first of all, realizing there is no inlet here. So our formula is, getting rid of the negative sign. See, now it makes very sense with the numbers we have given to understand the formula. Initially, our system had 10 kilogram water, then it became 7 because of 3 kilogram exiting. Okay, so these were numbers we gave to understand the formula. It is very important how you define your boundary because that way you can identify energy interactions. And this is our boundary, this rigid tank. Okay. So therefore we need to look at what is crossing the boundary to identify the energy interactions. Heat is getting in, mass is getting out. These are the only energy interactions. Now, very good. We understood the mass balance, wrote down the formula, and adjusted according to our current problem statement. Now the next thing is let's write down energy balance. In this case, energy balance in an unsteady flow device, energy getting in minus energy getting out is equal to the change in the energy of the system. Previously, we weren't dealing with systems energy in a steady flow device because in a steady flow device, your system's energy was not changing with respect to time. What we are interested was only energy interactions. But now we cannot eliminate the term that these energy interactions are actually causing a change in the energy of our system, and we need to study that. So as we talked about it, energies are getting in with heat and getting out with mass. And mass getting out is exiting mass. Inside though we have M1 changing into M2 due to mass interaction. 1 and 2 subscripts here define our state, and E defines our exit mass. Now mass is exiting as ME with an enthalpy HE. Okay, because exiting mass also has its own energy, and we define the energy of the flowing fluid, meaning the mass that is getting out with its enthalpy here. And then this causing a change in the energy of our system, but we have two different masses this time. It's unlike a closed system where mass was constant. Here in the unsteady flow device, mass is changing. So you need to define two different energies for the state, U2 and U1 here. Okay, so with that being said, now let's take a look at what they are asking for. They're asking for us to calculate the heat interaction. So that means I need to solve this equation. And let's first solve it for heat and finalize our formula. We just need to know M2, U2, M1, U1, and then MEHE. Okay, so this is our final energy balance. Now from here, we just have to now find the properties and masses. Let's take a look at how we can find the mass. Since this is a water, I cannot use ideal gas equations to calculate the mass, but interestingly they give us the volume as 0.3 meter cubed, and the volume is not going to change from one state to another because it's a tank. That is our system. And if I somehow know specific volume, and either at first or second state, I can calculate the mass because mass is volume times specific volume. Therefore, looking at the state, at state 1, let's write it down. Let me see. Looking at state 1 of our system, we are given that our, let me see, temperature is 200, and then the phase is saturated liquid. So this 2 is enough. You have a saturated liquid at 200 degrees Celsius. Look at the tables of water, table A4, to read what is the specific volume. It should be the specific volume of the saturated liquid at that temperature. And then later we will need the internal energy too when we are calculating the energy balance. So whatever you think initially will be important, read those from the tables. The next thing is we will need, so to calculate the mass, we just can formulate this right here, right now. We can say, if I want to find the mass at the initial state, I need to use the volume and then the specific volume at the first state. And the volume is given. And specific volume, you just read it from the tables and plug it in. and then it gives you 259.4. So initially this was your mass. Now, but the problem statement gives you another hint about energy and mass interactions. In other words, it says 1/2 of the total mass has been withdrawn. Okay, so that means half of it exited and the remaining, which is actually the half of it, will remain. So second state mass has to be the half of this volume. And of course, if you know M1 and M2, first state and second state, you can understand how much has to exit to obtain that number, right? So let's go to the next page. We know that ME was M1 minus M2. So initially it was 259.4 and 129.7 kilogram, and then the remaining should be the half of it. Okay. So now all your masses are known: M1, M2, exiting mass. Very good. So the next thing is we need to look at state properties at the second state, because we need information about the internal energy for the energy balance. Otherwise we cannot solve the energy balance. We need U2. So let's take a look at state 2. For the state 2, we are only given, actually what we know is the volume. Volume is not gonna change. And we are also given the temperature, because they say temperature doesn't change. So we have to then let's find a beautiful color for state 2. It's state 2 that would help us to look at the tables to read internal energy. We only know temperature. And we are not given any other property, but we should be able to find it. Otherwise, we cannot figure out the internal energy. And the hint is actually the volume, because now you know volume and you know the mass. You can find the specific property, specific internal energy. Let's solve it. In this side is that volume over, so first of all, remember that first state volume, second state volume is equal to each other, because we have a rigid tank. And if you want to find the specific internal specific volume at the second state, you're gonna divide the volume to mass. Since already know the mass, you can calculate it. Okay, so the volume is 0.3, and then the mass is 129.7. This is, I had something wrong with the units, I'm sorry. This is like that, and then this is like that, and then this should give you a specific volume of this. Okay, so now we know the specific volume and we know the temperature. We should be able to look at the right tables for state 2. Let's write it down. And when you do that, it is actually going to give you that you actually have a mixture. That means the specific volume you have is in between Vg and Vf for that temperature. Okay, so therefore, unfortunately, we just need to find quality, and with the use of quality we just have to find the internal energy. So let's start with finding the quality at the second state. To find the quality we need to know a specific property. In this case we know the specific volume at the second state. Remember, this is our formula. And then for that temperature we just have to read from our tables, water tables, what is the volume of Vf and Vfg, and then plug it in to our formula. So the V2 is already, we calculated that, and Vf we look at from the tables for that temperature, and then we know Vg from the tables, and then we have Vf. And the quality should be 0.009171. Okay, now let's calculate U2 then, because U2 is what we're gonna use in the energy balance. We need to look at this equation now. Through quality and the help of the tables, we can formulate and calculate our second state specific internal energy. This was quality, this is UFG, we read from the tables, and we calculated to be 866.46. Alright, now you actually have everything you need to be able to calculate the energy balance. Let's copy that energy balance into that page and plug in the numbers and solve it. Okay. So this is gonna be a long equation. So I'm gonna ignore the units, just gonna write the numbers. Okay. So M2 was 129.7. U2 was I'm sorry, M1, M2, U2, right? Okay, correct. So M2 was 129.7 and U2 was 866.46. We just calculated. M1 was 259.4 and U2 was 850, U1 was 850.49. And we actually forgot, we can do it now, but we need to check also exiting enthalpy, and I'm gonna talk about that, but let's write down first. Exiting enthalpy has to be the same as inlet enthalpy, because from the first state, exiting enthalpy has to be the same as first state enthalpy, because from the first state of that system you are releasing some amount of it, right? It has to be at the first state when you are releasing it, when it's exiting from the exit. So, but I will sketch it and show it to you. But first of all, let's write down what was ME. ME is 129.7. And then the the enthalpy at the exit is the same as inlet enthalpy. So for that we need to find it. Okay, I think we didn't find that one. Okay. Actually, let me describe it first and let me open up another state for that calculation. So let me first describe it, okay? So let's go to another. So this is our tank. Right? And it is at state 1, the water is. So when we open up the valve, now this water at state 1 is going to exit. So exiting properties has to be the same as state 1. Now because of this interaction, mass interaction, the state 1 water exited our system. We go to another state, okay? We close the valve. Because the mass already exited, now you are at a different state. Properties have changed. So basically, exiting properties has to be the same as state 1 properties. You can also open up property writing for the exit state, we can say, like this. And then what would be the temperature of the water at the exit? It has to be the same as the state properties as state 1. So it has to be at 200 degrees Celsius when it is exiting. Besides that, it has to be a saturated liquid when it is exiting, because it is carrying all those state 1 properties with it. So this tells you what our enthalpy is. It has to be the enthalpy of a saturated liquid at that temperature. So you write it down and find it from the tables. Now we're gonna go back and then plug this in back to our equation. All right. Okay. Okay, so if you do everything right in this way, let me check and make sure all the terms are correct here. Okay, it should give you 2,308 kilojoule. Okay, that's it.